In this video, we're going to learn about kinetic molecular theory. Kinetic molecular theory is a series of assumptions that we make about gases. The first of which is that gases consist of many particles that are spread far apart from one another relative to their own size. So when we look at this container with a few different gas particles, you can see that the gas particles are very small themselves, and they're really far apart from one another in this much larger container. The next assumption is that collisions between gas particles and between particles in the container that they're in, the walls of the container that they're in, those are elastic collisions, which is a term from physics. What we can take from this is that there is no kinetic energy lost during these collisions. There will be a certain kinetic energy as a mass is moving at a certain velocity, and when the particle with a certain mass and a certain velocity collides with another particle with a certain mass and velocity, the products of masses and velocities will still add up to be the same thing. There will not be a change in kinetic energy. There will not be a loss of kinetic energy during these collisions. The third assumption that we make is that gas particles are going to be in continuous random motion. They are not moving around with any order. They are totally random. And that relates to assumption number 4, which is that there are no forces of attraction between gas particles. When they collide, they simply bounce off of one another. They don't slow down and lose kinetic energy. They have these perfect collisions where kinetic energy remains constant. And although it may be true that gas particles are polar, some of them may be polar, because they're moving around so fast, we assume there are no attractions felt. They're moving very fast, and they're very far apart from each other, so they don't feel forces of attraction. The fifth assumption that we make is that the temperature of a gas depends on the kinetic energy of the particles of the gas. Actually, the temperature of a gas will be a distribution. It will be a distribution such that if this is the energy and the number of particles, we will find that at a certain temperature, we will get most will be within a certain range of energies, but there will be some particles with a lot of energy and some particles with very little. But what is energy? Kinetic energy is 1/2 mv squared. M is mass, and v is velocity. So the kinetic energy of a substance, let's take, for example, helium. Okay, helium, and let's compare that with xenon. Helium at one temperature and xenon at the same temperature, so that we have an equal comparison. They should have on average the same kinetic energy if they have the same temperature. But because we know helium has a small m, it has a smaller molar mass, every particle of helium is rather light. Xenon has a large m. In order for the kinetic energy of helium and the kinetic energy of xenon to be the same, because they're at the same temperature, in order for that to be the case, if helium has a smaller mass, it needs to have a faster velocity, and xenon needs to have a slower velocity. So that is something to take from this fifth assumption. Now, kinetic molecular theory does a very good job of explaining the physical properties of gases that we know. We know that gases will expand to occupy whatever their container may be. If you have gas in a tank, if you let it out of that tank, it will expand to fit whatever the room is that you're in, for example. So this comes from assumption 4 that particles move randomly in all directions and there's no attraction among them. So actually, sorry, it's assumptions 3 and 4. Random motion with no attraction holding them together gives us this property of expansion. They separate from one another. Fluidity is another thing. Just like liquids, gases are fluid. And this has to do with the particles really not having any attraction to one another whatsoever. They'll just slide right by each other or bump into each other and perfectly go in different directions. Gases also have a very low density. I know this because I don't have to struggle to swim through air. The particles are very far apart and they're very small relative to the volume they occupy. That is the definition of having a very low density. And this comes from assumption number 1. So, additionally, gases are very compressible. Again, because gases are far apart, based on assumption 1, there's room for them to be forced closer together. It causes pressure to increase, but it's possible to pack them in if we force them together. Diffusion also, particles move randomly in all directions, so a mixture of gas will result in an even distribution of all gas particles. If I look at the air in this room that I'm in, it consists of oxygen, more nitrogen than anything else, a little bit of argon, some water vapor. But it's not that over here there's a lot of water and over there there's a lot of nitrogen. Everything is evenly distributed. Just like diffusion that you learned in biology, if I have a drop of food coloring and I mix it with water and give it time, it will spread out so that the food coloring is evenly distributed across the whole solution of water. One more thing is that effusion. Effusion is a property of gases, and the rate of effusion is dependent on kinetic molecular theory as well. Effusion is the phenomenon of if we have gas in a box and we poke a hole in that box, gas particles will escape from that box. They'll go through a little hole. And the rate of this occurring, it depends on how fast the particles are moving, which at any given temperature depends on their mass, which goes back to our kinetic energy is equal to 1/2 mv squared. A lot of these properties we're going to come back to at a later time. Diffusion and effusion, for example, will come a little bit later. I do want to point out that real gases do not obey the kinetic molecular theory. If we do have high pressure and low temperature, gas particles will be very tightly packed, and so their volume, the volume that the particles themselves occupy, will actually be rather large relative to their container. So they will be closer together, and they will start to feel intermolecular forces as they're forced together. And as a result, their motion will no longer be random. In fact, you could potentially, with high enough pressure and low enough temperature, you can actually cause gases to no longer become gases. They could condense into the liquid phase or the solid phase, for that matter. But the stronger the intermolecular forces, the less ideal a gas will behave. So low idealness depends on the conditions, pressure and temperature, and also just the properties of the molecules themselves, how strong the IMFs are. So for example, water vapor will behave less ideally than helium due to water being very, very polar and having strong IMFs, and helium being completely nonpolar and having very weak IMFs. So H2O under the same conditions as helium will be less ideal, and helium will be more ideal. And ideal meaning obeying kinetic molecular theories, kinetic molecular theory, I should say. But also, conditions matter. the same gas under high pressure and low temperature will behave less according to KMT than the same gas at lower pressure and higher temperature. So that's kinetic molecular theory as a bit of a rundown. It's a bit of an introduction to a lot of things that we're going to study further in depth in the weeks to come. So I hope you've enjoyed this video. Let me know if you have any questions or comments in the comments section below. Thank you.